Nodal voltage analysis. Now this is the most important shortcut technique for solving the circuit problems rather than applying the Kirchhoff laws. So Kirchhoff laws, if we apply to the circuits, typically we end up with a lot of equations in lot of currents which we need to solve, and solving those simultaneous equations in 30 seconds or 60 seconds is not a very easy task. So we will be using, this would be our preferred method, the nodal or voltage analysis method would be our preferred method for solving these circuit problems. Okay, so note this down, listen to this method very carefully, and from now on I urge you to use this method instead of applying the Kirchhoff rules. Only if this method ends up being more complicated, then use the mesh analysis method or use the Kirchhoff method in that case. Okay, so now let us understand with this, what does the nodal voltage method mean? See, the nodal voltage method tries to find out the voltages at all of these nodes A, B, C, D, E in the circuit in order to solve a circuit problem. So whereas the Kirchhoff method relied on finding out the currents, in the nodal voltage method we would be finding out the voltages. Okay, so very simple. It is very simple task. To begin, the first step is to assign a voltage of 0 volt to one of the nodes. So this is to simplify our task, okay, because all the voltages in this circuit are relative. Okay, that's what you need to think about. Every time we think about a circuit, the voltages in that circuit are relative. So any one of those nodes in the circuit, I can just ground it. I can just say that the voltage there is 0, and then determine the voltages in rest of the nodes of the circuit with respect to this particular node which I have assigned to 0 volt. This 0 is a value that I choose for my convenience. This could have been chosen as 10 volts. You could choose it as 10 volts. All the other voltages would then increase by 10. But the thing is, we choose 0 volts because our equations come out to be simpler, and that is really what we really intend to do. Our equations, that simplify our equations. So I choose a value of 0 volt. Once I have done that, now I try to assign the voltage values to all the other nodes, as many as I can, based on this 0 volt voltage at the node E. So now this node A, since it's directly connected to node E, this will also be grounded, okay, because this wire is idle, there is no resistance here, so the voltage at both these nodes A and E has to be the same. Similarly goes for the negative terminal of this battery. Here also the voltage has to be 0 volt because it is directly tied to the 0 volt at this point, okay, and these wires are idle. So here also the voltage would be 0 volt. Voltage would, from here, if it's 0, this is a epsilon, EMF of this battery is epsilon. Therefore, the voltage here has to be epsilon. Okay, the voltage from here to here, it has to increase by 2 epsilon. So it goes from 0 to 2 epsilon. Since the voltage here is epsilon, the wire is ideal. So voltage at B would be epsilon. Voltage at D would be 2 epsilon. Now very simply, we have actually determined the voltage at in fact all the nodes of this circuit except for one node. Okay, there is a single node in the circuit at which the voltage remained undetermined, which is node C. So now let us focus our attention to node C. We want to find out the voltage there itself, there also. Okay, that is ultimately we need to find out this voltage, because that is the only unknown. If we find the voltage at node C, we can then find everything else in the circuit. We can find all the currents, anything. Okay, we have completely determined it. So we focus on the node C where the voltage is left undetermined. So here what do we do is that we assign currents coming into this node. So this is done using the Kirchhoff current law or the node rule. Okay, so notice that how I have assigned here 4 currents, and the equation for the node rule will be I1 is equal to I2 plus I3 plus I4. Okay, this is very simply the Kirchhoff current rule or the node rule that I have applied to this element. Now all of these I1s, I2s and I3s and I4s, all of these I's, I would write them in terms of the voltage VC. See, epsilon here is actually given as this is given as 200 volt. Okay, so this value is known. Okay, epsilon is actually known here. Similarly, the value of R is also known. It is given as 1 kilo ohm. For the purposes of this particular problem, we know the epsilon and R. They are not really unknowns. What is the unknown value? Vc. Okay, so what we have an equation at the node where the voltage is unknown, Vc. We write the current equation. And this current equation, I then try to write all of these currents in terms of the corresponding voltages. So I1, for example, what would be the value of I1? We know that current in a node I is equal to voltage divided by the resistance. So if the resistance is R, the voltage across the resistance is V across or V, then the current through the resistance would be I. So what would be I1? It is the voltage across this resistance, which is epsilon minus Vc. Okay, so at this end of R, at point B, the voltage is epsilon, and at this point, the voltage is Vc. So voltage across this resistance is what? Epsilon minus Vc divided by the resistance itself would give me the current through that resistance. Okay, so this is the simple formula that we would use. Okay, this is nothing complicated. Okay, the only thing that you have to note here is that the sign convention is if the current I1 is coming in this direction, the voltage I write it as the first I write the voltage from which the current is originating. So I write the voltage of the node from which current is originating. So here I have chosen the direction of current to be going this way. So this is the originating node. So I will write the voltage at B, which is epsilon. Then I subtract the voltage at C, which is the ending node for this current I1. So this is minus Vc. I write it as epsilon minus Vc. If the direction of the current were reversed, if I had chosen the reverse direction, okay, then I would write I1 as Vc minus epsilon. But for this direction, we write the origin node of the current minus the terminating node of the current divided by the resistance between the two nodes B and C. Okay, so this is what I1 is. Similarly, I can write the value of I2 as well. Very, very simple, nothing complicated. What is the value of I2? The starting point is Vc. The ending point for current is 0. Very, very simple, and this becomes divided by 4R. Now, similarly, I can write the value of I3. I3 becomes the starting point, which is Vc minus 0 divided by 3R. Now, at this point, you would quickly realize why our choosing of reference voltage or the grounding of the node E was so important. Our lot of our voltages here are coming out to be 0 when we are subtracting. Now, I4 here would be, of course, the starting, which is Vc, minus ending, which is 2 epsilon divided by 2R. Okay, very, very simple. So now we have I1, I2, I3 and I4. I can substitute these values in this equation, and you would quickly notice that my job becomes very, very easy as soon as I substitute epsilon minus Vc by R is equal to I2 is, I substitute value of I2 from here, which is Vc by 4R plus I3, which is Vc by 3R plus I4, which is Vc minus 2 epsilon divided by 2R. So here epsilon and R are all known. Okay, only unknown here is actually Vc. That is the only voltage that we were not able to determine, and that's the only unknown. In fact, R's would all just cancel out. So now we can find out Vc in terms of epsilon. So Vc, if you solve this equation, this is a single equation in a single variable. So whereas Kirchhoff laws would have given us 4 equations, 4 currents, we have to find out 4 equations in 4 unknowns. Using the nodal method, we only have a single equation that we need to solve. So much simpler, so much simpler. Okay, so with this, we can solve the value of Vc, and that comes out to be 24 by 25 epsilon. Okay, and epsilon we already know is 200 volt. You can substitute the value and determine the final value of Vc. Now, as soon as we determine the value of Vc, we can find the current I2. Okay, so the ultimate objective is to find the current from A to E. We really want to find this current I. That's what we want to find out. Okay, so if we had to find out the voltage VC, then we were done. Okay, but now we need to find out the current. So the current I is really equal to this I2 current is coming here and this I1 current is leaving from here. So current I is nothing but I2 minus I1. Okay, since we have determined the value of VC, we can determine the value of I2 and I1. Okay, so these two are also determined. I2 and I1 also I can determine very quickly. Okay, by substituting in these equations. Okay, here I know the R, I know the value of VC, I know the value of epsilon, so I can quickly find out value of I2 and I1, and from there I can find out the value of I, which would come out to be 50 milliampere if you were to solve it. Okay, but the ultimate thing here that I really want you to understand is that using this nodal voltage method, we were able to convert the 4 equations in 4 unknowns, the 4 currents, to a single equation in a single unknown, which was VC. And as soon as we were able to find the value of VC 24 by 25 epsilon, we were able to find that value. We will be able to quickly determine all the other currents and voltages in the circuit depending upon what we have been asked. Okay, so with this, now let us just summarize the voltage method. What are the steps to actually do this voltage method? See, the first step that we do is we select one node as the ground reference. So this was the ground reference. This is the node which has been grounded. Okay, there are 2 ways to symbolize that. And of course, the node which is grounded, we assign it the voltage of 0 volts to simplify our equations. Now we can write the all other voltages in terms of this ground voltage of 0 volt. We try to assign the voltages to all other nodes as much as we can. For those nodes which are now left out, for example, in the case of this node VC, C node was really left out. We didn't know the voltage here. So we assign a variable voltage here, VC, V1, V2, whatever you want to call it. And for that particular node, we write down the Kirchhoff current equation. For the nodes where we don't know the voltages, we write down the Kirchhoff current equation. We substitute the values of currents in terms of the voltages. So for example, for each of these currents, I1, I2, I3 and I4, we would write down their values in terms of the voltages, and so we get our equation in terms of voltages, and then we solve those equations. Okay, so those are the steps to be solving the problems using the Kirchhoff, using the node method or nodal voltages method. Now here is a slightly complicated example where what happen is we have two voltages which are unknown, right? So in this circuit, what would happen is that we have already grounded this. So this becomes 0 volt, this becomes 0 volt. The voltages at these points becomes 0. Voltage here is not really known. We will call it VD. Voltage here is also not known. Okay, we will call it VC. Voltage here is also not known. We will call it VB. And voltage here is also not known, VA. Okay, but the thing I want you to understand is that there are cases when this particular voltage source or a battery would appear between two unknown voltages. Okay, so in this case, what had happened is that our batteries were appearing, one of the nodes to which the battery was connected to, we had a known voltage, in this case 0 volt. Okay, so we knew that the other end of the battery would actually be at 0 volt plus 2 epsilon. In this case, that is not that is not the case. Here the battery is appearing between nodes for which we don't really have the equations. For these two nodes, we don't really know the voltages. So battery is appearing between the nodes for which we don't really know the voltages. So if that is the case, then what we do is that we combine this entire thing into a single node. Okay, we don't write separate nodal equations, we don't write separate current equations for this node B and this node C, but we write a single current equation for both taking into account both the node B and node C. So I'll show you how to do that here right now. Okay, so just just bear with me, okay. So here what I do is that I assign the currents any which way I want, okay. I can assign the currents in whichever direction I want. So I choose the direction of currents to be this way, okay. So the direction of, these are my direction of currents. So this is current I1, this is current I2, this is current I3, and this is current I4, okay. Here the total resistance becomes 9 ohm, and this is in series, and the voltage here is 0 volt. The voltage here is 0 volt, and this total resistance here is 8 plus 5, that is equal to 13 ohm. So I only have a single resistance here. Similarly, I only have a single resistance here of 9 ohm. I can combine those two resistances in series. Okay, of course you can do more series parallel game here, but let's not do that for a second. Let's just keep these nodes right here, okay. So now we just take the B and C all together. The first thing I do is that I assign the voltage at this particular node as V, okay. I just call the voltage at this particular node as V. Since the battery would increase the voltage by 8 volt, the voltage at B would be V plus 8. Okay, very simple. Okay, so I traverse the battery from minus to plus. So from V, the voltage would increase to V plus 8. So at B, I know the voltage. Now what about the current I1? See, first let us first write the equation for the current, all the currents. All the currents, I take them as 1. Okay, this battery I completely ignore. This battery I completely ignore when writing the current equation. I treat this B and C as the same node, as one and a single node when writing the current equation. So what would be the current equation in that case? It will be I1 minus I1, currents are leaving, minus I2, current is leaving, minus I3, current is leaving, minus I4, will be equal to 0. So I have written a single equation for all of those 4 currents. Whereas the voltages at B and C, I have taken them to be different, but I have taken this node as a single node for writing the current equation. Now that is where the difference really comes. When we have a battery whose either end on voltages on either end are actually unknown. So now what about I1? I1 is the current in this direction. So initially the voltage is V plus 8. Okay, all of these signs I can turn them to positive, just to simplify my job here. Okay, because here this is 0, I multiply everything by minus 1 if you will. So here this original current is V plus 8, the final current is 0. So this becomes V plus 8 minus 0, or just V plus 8 divided by total resistance in this arm is 9, and this plus I2. I2 is what? The current, the voltage here is V plus 8 divided by minus 0, okay, voltage here divided by 12, plus what about I3? I3 is this current, which is the voltage at this node. Voltage at C is actually V. Note the voltages I am taking to be different. Okay, I understand that at I1, when I am computing I1, I took the voltage to be V plus 8. Okay, when I am computing I3, I took the origin as node C and I took the voltage as V. And of course the terminal, the end point is minus 0, which I don't really write because minus 0 is of course 0 only, divided by the resistance, which is 4 ohm, plus I write down this last equation, which again comes out to be V minus 0 divided by 13, and this is equal to 0. Now you can solve for V. This is a single equation that you really need to solve. Now this was only for the purpose of illustrating that how we solve, how we apply the nodal voltages method when we have a battery and both the terminals of the battery have unknown voltages. Okay, that was the thing here to really understand. I assign voltage at one of the terminals, the negative terminal, as V. The voltage at the positive terminal will become V plus, in this case it was 8. In your case, whatever the EMF of the battery is, V plus the EMF of the battery, or epsilon. Okay. So this is how we apply, and from then on I then write the current equation taking this node and this node as one node. That is what I do in this in this case. Okay, so I took them as one node, I apply the current equation. So listen to this very carefully, because this is a slightly tricky thing. And then all those currents, like I did before, I write them in the form of the equation, I write all the currents, I express them in the terms of voltages, and when I do that, I take care that the voltages I am writing at this point, I am very careful that I write the voltage of the corresponding node. So I need to write the voltage of B when calculating the currents I1 and I2, and I took the voltages V plus 8 and not just V. Okay, so this was the thing when we had, this was how to apply the nodal voltages method when we had a battery with unknown voltages. Now here is another such example where we had we have again a battery with unknown voltage. I'll show that to you in a second. Now in this case, notice that we will again choose our one of the terminals as a reference terminal, that is the starting point. So this becomes 0 volt, this becomes 0 volt, this becomes 0 volt, this becomes -2 plus, so this becomes 14 volt. Okay, here is 0 volt, I traverse the battery, so this has to be 14 volt. So EI I also know. Now what voltages I don't really know at this point. At this point, I don't really know the voltage VB and VA. Of course, these are connected by a single wire, so the wire is the same. So the voltage here, I take it to be just V. At A also, the voltage becomes just V. So that is the only unknown voltage. V is the only unknown voltage. The thing is, again, by using this method of super node, okay, what I do is that as soon as I know the voltage at C, I know the voltage at B as well. So as soon as I know the voltage at this point, I call it V. Okay, this voltage here after an increase of 10 volt would really be V plus 10. Okay, so that is what I do. I traverse the battery and I assign the voltage there itself. Now this entire node, okay, this entire node, I write it as just one node. Now that is what the super node method is. I take it as a single node for the purposes of writing my current equation. Okay, so at this node the voltage is not known, so I really need to write the current equation for this point. That's what we know. So here I take the current as I1, here I take the current as I2, and here I take the current as I3. So I can write I1 is equal to I2 plus I3. Okay, notice that we would have had to solve for 3 currents had we used the Kirchhoff laws, but thanks to this method we only have a single voltage. So I1 is equal to, it's coming in this direction, so I write 14 minus voltage at this point V divided by 4. This is equal to I2, which is this one, V minus 0 volt, which is right here, okay, divided by the resistance, which is 2. Okay, this is the current I2, it's going in this direction, and then we come on to the current I3, which of course we know the resistance V, the voltage across the resistance is V plus 10 at one end and 0 at the other, divided by this one, the resistance itself, which is 6. Okay, so very simply we were able to use the nodal voltage method to get a single value for voltage. Now if you compute the value of voltage using this equation, this will come out to be 2 volt. We want to find out the current through 2 ohm resistor. This 2 ohm resistor, we all know that the voltage here is 2 volt. This current I2 will be equal to voltage across this resistance of 2 ohm. What is the voltage across this resistance of 2 ohm? The voltage across this resistance of 2 ohm is 2 volt divided by the resistance itself, which is 2. So the current is actually 1 ampere in the direction that we have given. So that was the objective of finding out, but the ultimate thing is that look how simple the equations are. Very simple. Okay, now you solve the same problem using the current rule. In fact, we have solved in one of the classes. Things will become quite complicated, unfortunately. So we will prefer to use the nodal voltages method as much as possible. Now here is a slightly tricky problem. Again, if you were to use the mesh rule or you were to use the Kirchhoff current rule, Kirchhoff laws directly, then this particular problem will become very complicated. Here we'll just solve it very simply. Okay, so it is not due to me, of course, it is due to this method. So I assign a 0 voltage to this particular node. I can do that. As soon as I assign 0 volt to this node, what would be the voltage here? It will be minus 40 because it's plus to minus, so there is a voltage drop here. What would be the voltage here? It's minus to plus, so there will be a voltage increase, 360. Okay, these are the voltages. And what would be the voltage here? Is plus to minus, it will be minus 80 volt. Okay, so I choose the 0 volt. At the top, you could have chosen the 0 volt. At the bottom, in fact, you can try to do that also. It will not make things more, it will make things only slightly more complicated, but not very hard also. So now, there are 4 branches really here. So, of course, I know that there will be 4 currents here. So, let us just assign this current as I1. This current becomes I2. This current becomes I3. And this current becomes I4. Okay. I can simply write the voltage here at this node is not really known. We call it the voltage V. Okay. This is a single node. It is connected by an ideal wire. So, voltage across this entire thing is V. At the top, we know the voltage is 0. At the bottom, the voltage is we don't really know. We call it V. Of course, because we don't really know this voltage, we have to write the Kirchhoff current rule for this particular node. This is a single node. Okay, this is a single node. Okay, for this node, we will be writing the Kirchhoff current rule. What is the Kirchhoff current rule for this node? It is I1 is equal to I2 plus I3 plus I4. Very simple, nothing complicated. Okay, single equation is coming. Now, what about the current I1? It is coming from here. So, we write, which implies that it is 360 minus, we know voltage here is V, divided by 20. That is equal to, what about the current I2? The current I2 is going from here, which is V. And where is it going? It's going to minus 40. So, minus of minus 40, which becomes plus 40, divided by 80. Plus, what about I3? I3, we know it's going here. It's starting from voltage of V and it's going to a voltage of 0. So, nothing comes at the top. V minus 0, you can write it like this if you want, but really it's just V. So, it becomes 20 plus this I4, which starts from a voltage of V. Again, it starts from voltage of V. And this current I4 goes to which voltage? Minus 80. Minus of minus is plus. So, I write it like this, divided by 70. Single equation, one simple equation in terms of V. Look how beautiful it looks, how simple it looks. Okay, you can solve using this. You can solve for the value of V. If you were to do that, then the value of V would come out to be 200 volt. Okay, so now we know the value of V, that is equal to the 200 volt. So, voltage here is 200 volt. We really need to find out the current through 200 ohm resistor, which is our current I3. That is what we want to really find out. Okay, so what about the current I3? We already have its equation right here. Okay, this current I3 is there. Oh, sorry, this should have been 200. Okay, V by 200. I made a mistake here. Okay, just please note that. So then current I3 becomes V. We already know 200 divided by 200, and this is 200 ohm, and this comes out to be 1 ampere. Very simple. Okay, nothing complicated. So this would be our preferred method because it yields the nodal voltage analysis yields fewer equations, most of the time a single equation which we need to solve, and the equation is also sometimes much simpler than the simultaneous equation that Kirchhoff rules yield us. So here, what is the main difference? We are solving for voltages instead of currents. The second thing is that we only use the current rule for those nodes where the voltage we don't really know. Where the voltage is unknown, we use the current rule, Kirchhoff current rule at those nodes. We are not using the mesh rule at all, and that is actually another simplifying factor, because using the mesh rule slightly complicates things. There are a lot of sign things that you need to take care of the signs, and that sometimes students make mistake there. So that's another simplifying factor. So this nodal analysis is really useful for branchy circuits, for circuits which have many loops, for circuits which are looped very parallel circuits, and in those parallel kind of circuits, right? For example, this was a very parallel circuit. We have very few voltages which remain unknown. Okay, so for these kinds of circuits, the nodal analysis is much simpler. But the methodology that you would need to follow is that always start with nodal analysis. Try to see how many unknown voltages you get. Only if you get many unknown voltages, go to the mesh analysis. And typically will use only these two methods. Of course, the first thing we try is to simplify the resistance in series and parallel as much as possible. Once you have done that, first the node analysis, then the mesh analysis is something that we are going to use. Okay, so we'll take several examples in subsequent classes in order to understand which circuit is best solved by which method. So definitely do subscribe to the channel and put your doubts in the comment section below, and we'll be very happy to look at those, and definitely do practice. Okay, good luck.